Section: Introduction. In this section, we delve into the realm of artificial intelligence, AI, and the ongoing issue of adversarial attacks, especially those aimed at neural networks. These attacks exploit weaknesses in AI systems, leading to compromised results and raising concerns about their reliability and safety. Despite efforts to address this issue, current defenses have struggled to find a balance between robustness against attacks and maintaining model performance. This trade-off between security and utility is widely acknowledged as a significant challenge. The emergence of generative models, such as large language models, LLMs, has added complexity to this problem. These models can generate sensitive information or harmful content, posing risks when deployed. While efforts have been made to align models with ethical standards through training, adversaries can still find ways to bypass these safeguards using adversarial attacks. This vulnerability to attacks that disrupt alignment poses a serious threat to the reliability and safety of AI systems, especially when facing determined adversaries. To address the limitations of existing defenses, we propose a novel approach called short-circuiting. Instead of focusing on patching specific vulnerabilities, our method aims to prevent models from producing harmful outputs in the first place. By using representation engineering, we reroute the internal processes of the model when it tries to generate harmful content, effectively stopping the generation process. This approach is attack-agnostic, meaning it does not rely on specific attack knowledge and does not require additional training or complex defenses. Our experiments show that short-circuiting, specifically representation rerouting, RR, significantly improves the alignment and safety of LLMs, even against unseen adversarial attacks. Compared to traditional refusal training and adversarial training, our method achieves better results with minimal impact on model performance. By combining short-circuiting with other control techniques, we develop a more advanced model called Signet, which not only enhances the model's capabilities but also drastically reduces the production of harmful outputs, even in the face of unexpected attacks. Our approach represents a significant advancement in balancing model capability and harmlessness for LLMs, demonstrating that it is possible to manage these trade-offs effectively. When applied to multimodal models and AI agents, short-circuiting shows promising results in improving safety and robustness against various attacks. This new paradigm offers hope in the ongoing battle against adversarial threats, paving the way for the deployment of more secure and reliable AI systems in real-world scenarios. Section Summary. The section discusses the persistent threat of adversarial attacks on AI systems, particularly neural networks, and the challenges in achieving high reliability without compromising model performance. A novel approach called short-circuiting is proposed to make models safer by interrupting the generation of harmful outputs directly, rather than focusing on specific vulnerabilities or adversarial training. This method significantly improves the alignment and harmlessness of large language models, LLMs, against various adversarial attacks, showcasing a promising path towards deploying robust AI systems without sacrificing capability. Section: Short-circuiting with representation engineering. In this section, we introduce a new method to reduce harmful outputs in neural networks by inducing short-circuiting. Short-circuiting involves redirecting model representations related to harmful processes towards incoherent or refusal representations. Our goal is to prevent the model from generating harmful behaviors. We focus on generative models like language and multimodal agents because they involve multi-step processes to produce outputs. By disrupting adversarial control across these steps, we aim to make the model more robust to attacks. Instead of just detecting attacks, we aim to disrupt the processes that lead to harmful outputs. We achieve this by remapping model representations that lead to harmful outputs, directing them towards incoherent or refusal representations, which is short-circuiting. This method can work across various inputs that may trigger harmful processes without needing to identify all potential inputs. Short-circuiting can prevent the generation of harmful outputs in general or more specific types like private information. It can be applied to different neural network architectures by using datasets and loss functions. One technique, called representation rerouting, RR, uses low-rank representation adaptation, LoRa, for short-circuiting. The training data for RR is divided into the short-circuit set and the retain set. The short-circuit set contains examples that may lead to harmful behaviors, prompting the short-circuiting mechanism, while the retain set includes examples to maintain desirable model representations. The quality of the short-circuiting mechanism depends on how well the data can elicit the targeted representations. The losses for the datasets are the representation rerouting loss and retain loss. The representation rerouting loss aims to remap representations from harmful processes to a desired target representation, while the retain loss maintains representations within a retain set. Different forms of the rerouting loss can be used, such as routing the targeted representation to a random direction or optimizing the short-circuited representation to be orthogonal to the original harmful representation. We find that optimizing for orthogonality is the most intuitive and effective approach. Overall, short-circuiting techniques can be versatile in preventing harmful outputs and can be tailored to different neural network architectures. Additional design considerations are discussed for further exploration. Section Summary. In this section, we introduce a novel approach called short-circuiting to prevent neural networks from generating harmful outputs by redirecting representations related to harmful processes towards incoherent or refusal representations. Our method focuses on disrupting adversarial control of multi-step processes in generative models, such as language agents, rather than just detecting attacks. By using techniques like low-rank representation adaptation, LoRa, in representation rerouting, RR, we partition training data into short-circuit and retain sets to control harmful processes and maintain desirable model representations, ultimately improving model performance. Section: Experiments. In this section, we conducted experiments using large language models and explored the concept of short-circuiting. We applied similar short-circuiting techniques to both the Mistral 7B Instruct v2 and Llama 3-8B Instruct models. The datasets used included UltraChat for instructional conversations and XS Test for exaggerated refusal scenarios. For the Llama 3 model, we added extra refusal data points to the dataset. We implemented representation rerouting, RR, and selected hyperparameters based on static attack test cases from Harmbench's validation set. To evaluate the models, we used Harmbench, which includes various harmful behaviors and a range of black box and white box attacks. We tested the models against strong attacks such as gradient-based optimization, LLM optimizers, and custom jailbreaking pipelines. Additionally, we introduced a multilingual attack and 3 powerful attacks that manipulate system-level and representation space access. We assessed the capabilities of the short-circuited models on MT-Bench for instruction following abilities and the Open LLM leaderboard for knowledge and reasoning tasks. We compared our models with the original Mistral and Llama 3 Instruct models, as well as the R2D2 model. Our results showed that our RR technique significantly reduced compliance rates to harmful requests by an average of 87% with Mistral and 90% with Llama 3. Unlike the Mistral R2D2 model, which had limited generalization to various attacks, our approach focused on hindering harmful content generation without the need for specific attack training. We also explored short-circuiting in multimodal models by combining datasets and applying RR to LLAVA next Mistral 7B. Evaluating the robustness of these models, we generated adversarial images using a white box approach and observed a significant increase in robustness while maintaining model capabilities. Our results demonstrated a reduction in compliance rates to harmful prompts by 84% compared to the original model and 85% compared to a safety prompt, with minimal impact on model capabilities. This approach shows promise in enhancing the robustness of multimodal systems against harmful inputs. Section Summary. In this section, we conduct experiments on large language models using short-circuiting techniques. We evaluate the harmfulness of the models through various attacks and observe that our short-circuiting method, representation rerouting, RR, significantly reduces compliance rates to harmful requests by an average of 87% with Mistral and 90% with Llama 3, showcasing strong generalization across diverse attacks without specific training. Additionally, when applying RR to multimodal models, we achieve a notable increase in robustness against harmful prompts while maintaining model capabilities, demonstrating the effectiveness of short-circuiting and enhancing model resilience without compromising performance. Section: AI Agents. In this section, we mixed the short-circuit and retained datasets from our experiments with function calling short-circuited and retained dataset. The detailed process of generating the function calling short-circuited and retained dataset is described in the appendix. We also used the same hyperparameter configuration as in our experiments for the short-circuited LLMs. To evaluate the effectiveness of RR in preventing AI agents from making harmful function calls, we created a dataset with 100 requests designed to trigger harmful actions through function calls, along with associated function definitions covering various categories like cybercrime, disinformation, fraud, and harassment. We tested the model's compliance with harmful requests under standard settings and forced function calling scenarios. Forced function calling is similar to a pre-filling attack and is supported by major model providers. For capabilities evaluation, we used the Berkeley Function Calling Leaderboard, BFCL, and observed that our model became more robust to harmful function calling requests after applying RR, reducing harmful action compliance rates significantly compared to baselines. The short-circuited model also maintained its performance on the BFCL. This demonstrates the method's effectiveness in controlling agent behaviors under pressure and in environments with reward biases, potentially mitigating harms like power seeking or dishonesty by adjusting the short-circuit set. In our ablation and analysis, we conducted pairwise ablations for each component of the RR loss. Augmenting the short-circuit set with requests that bypass refusal mechanisms decreased OSR while maintaining capabilities. Removing the refusal retain component increased relative robustness but degraded capabilities. We experimented with different loss functions and found that the cosine loss proposed in RR offered more stability than others. Analyzing the training data composition, we split the data into categories of harm to train category-specific models and measure their generalization performance across categories. We found strong in-domain generalization and observed that training on broader categories offered greater generalization than narrower ones. In our representation analysis, we compared the representations of the standard versus short-circuited models for harmful responses. We observed significant changes in cosines and norms during prefilling, starting from layer 10, which is where short-circuiting occurs. We noted that representation norms often increased after short-circuiting. Our proposed method had the intended effect on representations, allowing us to detect short-circuiting by analyzing internal representations, which could lead to system-level mitigations.